4, we were talking about the zeros of polynomial functions. And I want you to remember that when we talk about a zero, we are talking about a solution. If we set an equation equal to 0, then we're talking about the solution. If we're talking about it in terms of a graph, then a 0 is, you know, the place where it crosses the x-axis. So there are x-intercepts also. So we call this same word is used for several different things, depending on what application we're talking about. But the process for finding it is the same. So if it asks for a solution, or if it asks for a 0, or if it asks for an x-intercept of a polynomial function, you're going to do the same process. Okay, we're talking about zeros right now because we are talking about graphs. This whole chapter is about graphing different types of functions. So when you talk about the zeros of a polynomial function, we're going to be using those ideas from last section with synthetic division mostly. Okay. The problem is that on the homework, the one that when I did it, you know, remember 43, when it told us that some number was a 0, so I knew that I could start there. Most of the time we don't know where to start. And so the very first thing we talk about is the rational root theorem, or rational zero theorem, depending on what book you're looking in. And it's got a whole bunch of words in it. I'm just going to kind of boil it down to what it means. If we have a number that's a factor of the constant term divided by a number that's a factor of the leading coefficient. And remember, we are talking about rational roots, right? So it could be a fraction. So factors of the constant term divided by all the factors of the leading term give us all of our possible rational roots, or zeros. They call them zeros in this book. Okay? Can't have anything else. The other zeros that you might possibly get are things that are not rational, so irrational numbers and some maybe even complex numbers, imaginary numbers. Okay, so I'm not saying it's all the roots, but it's all the possible rational roots where we could do synthetic division with it nicely. Okay, so checkpoint 1 says for us to find all the possible rational roots of f of x is equal to x to the third plus 2x squared minus 5x minus 6. So we're supposed to list all possible rational zeros. This is how you do it. You just take all the factors of the constant term. The constant term is this one down here, right? So negative 6. Positive and negative 1 divide evenly into it, right? Positive and negative 2 divide evenly into it. Positive and negative 3 divide evenly into it. And positive and negative 6 divide evenly into it. Okay? And that's always divided by the factors of the leading coefficient. In this case, it's just 1. That's nice. I don't have to check a whole bunch of things. Just positive and negative 1. Okay? So the only thing that's possible, the only numbers that are possible are positive and negative 1, 2, 3, and 6. So there are 8 things. That's all I have to check with my synthetic division to look and see if there's a rational root. Well, yes, theoretically you might have to do it 8 times because the 8th one might be the one that you find that actually works. Hopefully not, and I will tell you that, you know, for me, as I was doing this in college algebra, I found that I was getting better at guessing which one to try. So, and I have some other rules that we're going to kind of put together with this so that you'll know whether to try positive or negative numbers. And that kind of narrows it down too. Okay? And I'll just tell you the truth, a whole lot of people cheat, and they go ahead and look at the graph, and they look at these numbers and see which one, yeah. And then they go ahead and put it in the synthetic formula, do the synthetic division with it to prove that it actually is the right one. So, it doesn't really matter. Okay. Checkpoint 2. This one's got a little bit more. Again, we're going to list all possible rational roots of f of x is equal to 4x to the 5th plus 12x to the 4th minus x minus 3. So what are the factors of the negative 3? Plus minus 1 and 3. And the factors of 4? 1, 2, and 4. And positive and negative always of all of them, right? So this is how you do this, or this is how I do this. Because I get turned around and I can't remember which ones I've done. All possible rational zeros are what we're trying to get here. So I take the 1 and I put it over 1. So positive, negative 1 over 1, 1 over 2, and 1 over 4. Now I take the next number in my list, and I got 3 over 1, 3 over 2, and 3 over 4. Okay. And that's my list. So you have to take everything on the top over every possibility on the denominator. So see, I took the 1 with the 1, the 1 with the 2, and the 1 with the 4. And I took the 3 with the 1, the 3 with the 2, and the 3 with the 4. That's my answer. Those are all the possible rational zeros. There are no others. There may be other zeros, but they'll either be irrational or complex numbers with an imaginary number part. Any questions about that? So, since we know now what our possibilities are to try, the second objective in this section wants us to actually find all zeros of these polynomials. So, checkpoint 3, we're going to find all zeros of f of x equal to x to the third plus 8x squared plus x to the third plus 8x squared plus 11x minus 20. So, first things first, because we don't want to just be trying everything in the world, right? So we're going to take all the factors of negative 20. 1, 2, 3 doesn't go into it, 4 does, 5, 10, and 20 over 1. So I do have several here, 1, 2, 3, 4, 5, 6, so 12 possibilities for answers. So I'm just going to tell you the truth. I normally, try 1. I like 1. It's easy. It's quick. And I kind of see which way I'm going. So I'm just going to try positive 1 to see if that's a 0. And so I've got 1, 8, 11, and negative 20. Bring down the 1. 1 times 1 is 1. That gives me 9. 9, and that gives me 20. And that is so nice when that happens. Sweet. Okay. That's right. That's what it means that it's a zeros, because when I plug this value in, I get a function value of 0. Well, you don't have to try them all. One of the things that we're going to talk about in just a minute is that the fundamental theorem of algebra tells me that I can't have but 3 solutions. Okay? So once you find 3 solutions, you're done with this problem. Now, once you get to here, I want you to think about the fact that, remember, we started with x to the third. So this is, if I rewrote that, that's x squared plus 9x plus 20, right? Okay? Once you get to here, you don't have to do synthetic division anymore, because now I know that this is A, this is B, and this is C. And it's just as quick a lot of times to go ahead and put it in the quadratic formula at this point and find your last two zeros. Because a lot of times those last two zeros are going to be the imaginary numbers or the irrational numbers and things that I couldn't get with a rational zero anyway. So once I get it down to the point where there's just three things in a zero, then I can go straight to the quadratic formula. So I know one of my zeros is 1. I got to find the other two, because I know I've got two more. Okay. So, depending on what you like to do, but I'm going to go ahead and I'm going to use the quadratic formula. So I got negative 9 plus or minus the square root of 1, isn't it? Because 9 squared is 81 minus 80 would be 1 over 2. So x is equal to negative 9 plus 1 over 2 and negative 9 minus 1 over 2. So I could have gone ahead and gone through my list and probably found these numbers. But, so that's 8 over 2, which is negative 4, and negative 10 over 2, which is negative 5. So those are my other two zeros. And again, you could have gone ahead and tried some other things for the synthetic division. Let me tell you how you do that while we're here. In case you don't want to do the quadratic formula, or you have something bigger and you got to do synthetic division again. You never go back to the original one. The next time you try this, what you do is you try one. Here's the constant, right? Here's the leading coefficient, so I only need the things that are going to 20. Didn't help me a whole lot on this one. And so then you pick one of these to try. So we'll try maybe negative 4. Try not to be so sloppy. Okay, and so you put the negative 4 into the result that you got from the first set of synthetic division, because what you're going to want to do is reduce every time. So don't go back to the original and try negative 4, okay? You understand what I'm saying to you? And see what would happen here is you get 1, negative 4, you get 5, negative 20 would give you 0. And then this says x plus 5 is equal to 0, so x is also negative 5. Because once you get to here, I mean, there's no sense in doing synthetic division again. Everybody understand how you can go, you can keep going down? Yep. Because the leading term is to the power of 3, and we're going to talk about that in a minute, but there's a theorem that tells us that. We always have that many zeros. Whatever that number is, we always have that many zeros. Now that does count multiplicity, and it does count, irrational numbers and imaginary numbers, but you will have that many zeros. They're just not all real numbers. They're not all, I guess I say zeros. They're not all x-intercepts, but they're all zeros. Okay? I'll show you on this one right here. We've got f of x is equal to x to the third plus x squared minus 5x minus 2. Okay, so my possibilities are plus or minus 1, plus or minus 2, right? That's all I got. I got no other possibilities for rational roots. With me? Because here's 1, so it's over 1. It doesn't change anything. So I'm going to try positive 1 again. A 1, 1, negative 5, negative 2 are my coefficients. Bring down the 1. 1 times 1 is 1. So I've got 2. 2 gives me negative 3. So that obviously is not a 0. So I throw the positive 1 possibility away. And then I try negative 1. Bring down the 1. Negative 1 times 1 is negative 1, so I get a 0. And I get a 0, because anything times 0 is 0, right? And I get negative 5 when I add. And a positive 5, and that's not it either, right? So positive 1 and negative 1, neither one work. So we're going to try 2. I'm going to try positive 2 or negative 2 first. Negative 2. 1, 1, negative 5, and negative 2. Bring down the 1. I get negative 2. That gives me negative 1 when I add. Positive 2 when I multiply. Negative 3 when I add. 6. That's not it. So we'll try positive 2. It's not positive 2 either. Okay, so positive 2 does work. But now we have attempted to use every single one of the other ones, right? I can't do synthetic division again because I don't have anything new to try. Because see, look, the only thing that works here that I can try is positive and negative 1, right? Leading coefficient, constant, 1 and 1. And I've already tried negative 1 and positive 1, and I got zeros for both. I mean, not zeros for both of them, right? So the only thing I can do at this point is I have to do the quadratic formula. So and this one's A, this one's B, and this one's C, right? Because they're in order. So I get negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 1 over 2 times 1. So I got negative 3 plus or minus the square root of 9 minus 4, which is 5 over 2. That's one of those irrational numbers that I was talking about, right? That's it. Okay. So my solutions are positive 2, negative 3 plus the square root of 5 over 2, and negative 3 minus the square root of 5 over 2. So like I say, there are times when you can't do synthetic division to find all the roots because they're not all rational. Now let's take this a step further and let's talk about solving. So we've been finding zeros, right? So now let's talk about solving a polynomial equation. So objective 3. X to the 4th minus 6x to the 3rd plus 22x squared minus 30x plus 13 equals 0. So, again, rational theorem says what? Possible rational zeros. Factors of 13. Divided by the factors of the leading coefficient. So the only thing that I've got possibilities here, positive negative 1, positive negative 13. Because remember, if I'm solving this, a solution, anytime I've got an exponent more than 1, then I always have to have it set equal to 0, and I have to get it into factored form, right? So, well, we could try to group it, but I've got 1, 2, 3, 4, 5. I don't even have an even number of them. That's not going to help. What we have to do in this case to get that in factored form is we have to find those zeros. Because remember from Algebra 2, my factors are always x minus whatever my zero was. Okay? My solution is the same as my zero. That's what I said to you at the beginning of this. Solutions and zeros are the same, and the process to find them is the same. They're just used in different situations. Zeros are talking about being able to graph it, and solutions are talking about solving it. But it's still the same process. Okay? So, I'm just going to do the same thing I've been doing. Positive 1, 1, negative 6, positive 22, negative 30, positive 13. 1, multiply, get 1, gives me negative 5. That gives me 17, right? 22 minus 5, 17. And that's 17, so I get minus 13, which gives me a nice 0. But I am not finished, right? I got to find the other zeros. And I can't put it in the quadratic formula yet either. So my only option is to try to do the synthetic division again. So I still got I need something that's divisible, factor of 13 divided by factor of 1. So I can try any of these again. And do remember that we can have multiplicity of more than 1, right? So just because I've used positive 1 already and it worked doesn't mean that I can't use positive 1 again and get another good answer. Did you hear what I just said? Remember, you can have the same root more than once. Remember, it bounces off if there's 2 of them. Kind of comes down and touches it and bounces right back off. Okay? We've already talked about multiplicities. That was in section 3.2. Right? Y'all remember that? We talked about it. When you put it in factored form, sometimes it looks like this. X plus 1 squared times x minus 3 times x plus 4. Right? So this one's got a multiplicity of 2. Because I just used it twice. Okay? Same thing could happen here. That's what I'm saying. So just because you've used positive 1 time and gotten a solution doesn't mean that it might not be used again. So I've still got 4 things I need to check for this section. For this result here. So I'm going to try positive 1 again. Okay. And it did work, right? So now I got to find the last 2. Now I can just put it in the quadratic formula, or we can try to we can try to use the synthetic division again. But like I say, at this point, I no longer like to guess and check things. I like to just plug it in the quadratic formula and be finished with it. So that's what you're normally going to see me do. You can go ahead and do whatever you want to do. So I got 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 13 over 2 times 1. So x is equal to 4 plus or minus the square root. And that's 16 minus 52. 4 squared is 16. And 4 times 13 is 52, if I'm not mistaken. So would it have done any good for me to continue trying to use synthetic division? Because this is going to be a negative number underneath here, right? Which is, and that's actually a negative 36, right? So you remember from quadratic stuff from chapter 2, how do I solve that? What does that look like? 4 plus and minus 6i divided by 2, which reduces down to 2 plus or minus 3i. So my solutions are 1 and another 1 if you want to write it, but it only has to be written once. You might want to, remind yourself that that's multiplicity 2. So I am going to come down to 1 and touch it and bounce back off, right? and then 2 plus 3i, and 2 minus 3i. Now, like I say, the next thing that we talk about is called the fundamental theorem of algebra. And it says that we can prove, and they go through the book and they show you the proof, that every polynomial that has a degree that's more than 1 has at least one complex zero. Well, remember that this number here that's a real number is also a complex number, right? Do y'all remember when we did complex numbers, we could write that as 1 plus 0 times I and put it in the complex number set. A plus bi is the complex number set. So when you extend that, what you get is this theorem or this corollary, whatever you want to call it, that says that whatever my exponent is on my leading term, that's how many zeros I have. Some of them got imaginary numbers in them. Sometimes, like the last one, they were irrational numbers, and sometimes they're rational numbers, but you're going to have that many regardless. The next part of that happens is that we talked about this before, anytime I have 2 plus 3i as a root, what has to go with it? 2 minus 3i. Do y'all remember that's called complex conjugates? Remember when we talked about that before? Yeah. They're the same numbers. The only thing that's changed is the sign in front of the imaginary number part. Every time. If I tell you that 2 plus 3i is a root on a test, then you're going to automatically, if I ask you to list all the zeros, you're automatically going to find a list that has 2 plus 3i and 2 minus 3i. I mean, you're just going to automatically know. The minute you see an I in there, its complex conjugate is also in the list. It has to be. Otherwise, how would they multiply back together and give me something that didn't have an I in it to start with, right? Did we have an I in the problem to start with? They must have canceled out, right? And that's how they canceled out, was with this idea of complex conjugates. Okay? And so those are all ideas that we've talked about before. Now, the next objective and the last objective, well, maybe I fibbed. There's 5 objectives, so we're on 4. We're almost through. Is the linear factorization theorem. Yep.
Whenever you're going to use synthetic division
Mhm.
to find the first zero,
Mhm.
you have to make sure like you have the right exponent, like if it's going to be working for that.
Mhm. Yep. Anybody else got a question? All right. The linear factorization theorem just says that if I have this in factored form, where it's x minus a 0, and in the book they call it c of 1, and x minus c2, and x minus c sub 3, and you say that equals to 0, then I can solve it, right? The big thing that you need to get out of this is, and remember, is that if I tell you that you have a 0 of 4, then the factor that goes with that is x minus 4. Everybody hear what I just said? Where C1, C sub 2, and C sub 3 are zeros of the function. So what you need to see from this, the big idea here, is that it's x minus whatever the 0 is. So if your 0 is negative 3, then your factor is x minus negative 3, which is really what? X plus 3, right? Because minus a negative, we're going to write it as a plus. Yes? Okay. Okay, so we're going to work backwards here is what we're going to do. Check point 6. That's when we use this idea. Check 26 tells us to find a third degree polynomial function. Call it f of x with real coefficients that has -3 and I as zeros, such that f of 1 is equal to 8. Okay, so this time they told me the zeros, right? And I'm supposed to come up with the function. Before, they were giving me the function, and I'm finding zeros, right? So we're going to use this linear factorization theorem because what did I just get through telling you? F of x is going to be equal to sum A, we don't know what that coefficient is, times x minus the first zero, x minus the second zero, and x minus the third zero. Now, why did I know I had 3 zeros? No. Because it says third degree polynomial. And I know that that means I got 3 roots, right? And if I have 3 roots, then I've got 3 factors, or 3 zeros. Some books I call them roots, some books I call them zeros. Okay? Everybody understand what I just said? Okay. Now it's always x minus, and that tells me I've got a root, or a zero of -3, so I'm going to plug -3 in there. Okay? And I got I, so I'm going to put an I in there. Ooh, I'm missing one. -I. Why is it -I? Complex conjugate. It has to have its conjugate every single time, and the way that you come up with the conjugate is you change the sign of the imaginary number part. Not the real number part, but the imaginary number part. This one didn't have a real number part in it, so I didn't have to worry about it. Okay? Now, so this tells me that f of x is equal to a times x plus 3 times x plus I times x minus I. Kind of got those out of order there, sorry. Ah, yes. You're exactly right. We do want to multiply these two together first because I want to get rid of those i's. So I have that f of x is equal to a times x plus 3 times, and then like Courtney said, I'm going to have x times x, which gives me x squared. This ix and this negative ix can cancel each other out, right? That's why they have to have complex conjugate pairs, because the inner and outer terms always cancel out. And then minus I squared, which turns into plus 1, exactly like Courtney said. Okay? Everybody see it? I squared is always turned into -1. So it's minus -1, which turns it into plus 1. Is that better? It does. So I got the square root of -1 times the square root of -1, which gives me -1. Okay, good deal. Shh. Stop all talking. All right. Now, we're going to distribute here and multiply all that stuff together. So I've got f of x is equal to a times, I get x to the third plus x plus 3x squared plus 3. Kind of not in descending order there. Wait, I'm not finished with this problem yet because I don't know what a is. Anybody, do we got another piece of information so we can find a? Is there another piece of information that we were given that we haven't used yet? F of 1 equals 8. So that means that I have this point 1, 8, right? So everywhere there's an X, I'm going to put in a 1. And everywhere there's an f of X, I'm going to put in a 8. So this is 8 is equal to a times 1 to the third plus 1 plus 3 times 1 squared plus 3. And you finish that, you find 8, and then you plug that in and you distribute it through and you're finished with that problem. Okay? The homework assignment is on page 371. It's 3 through 51 multiples of 3. So on page 371, 3 through 51 multiples of 3. Okay?